Hi, I'm Luis Kirsch from the Swiss AI Lab ICML. In this paper on self-referential meta-learning, we explore methods that modify and learn to improve themselves without explicit meta-optimization. A lot of machine learning is about designing learning algorithms that prescribe how to update a model or policy. Instead, in meta-learning at AutoML, we optimize over the space of learning algorithms. Unfortunately, this creates a dependency on human engineering on the meta level, where researchers now have to design meta-learning algorithms. Of course, instead of designing that meta-learning algorithm, we could continue that hierarchy and also meta-meta-learn the meta-learning algorithm. But what does that buy us? Ultimately, we seek a process of self-improvement that reduces our reliance on human engineering to the largest extent possible. In the best case, we don't need any fixed scheme of how to perform meta-optimization. But how can we avoid that while still guaranteeing improvement of the model? This is the question we investigate in this paper. Self-referential meta-learning answers some of these questions. The central idea is that there's a single function which defines the learning algorithm and model or policy. Here we focus on neural implementations of that. Basically, this neural network updates itself. This means that all the activations and parameters of that network can be updated by the network itself. We simply call these variables. Such a system can in principle not only learn a good model or policy, but also meta-learn, meta-meta-learn, and so on. The first challenge with such a system is how to access all its variables. In a standard neural network, there are O of n time varying activations and O of n squared fixed weights. For the network to control all of its variables, including all its own weights, it needs to generate O of n squared updates. Possible solutions to this issue are outer products that generate n squared variables from two n variables. This is done by reusing each activation n times, a kind of variable sharing. We can also share elements of the n squared weights and specify the weight matrix. Finally, the n squared weights can be used multiple times with different inputs. For more general analysis of this issue and the specific implementation we used, refer to our paper. Unfortunately, with a self-referential approach that can access all its weights, the problem is not solved. Because does the system actually reduce our reliance on human engineering on the meta level? In fact, it simply shifts the problem to finding an initialization of our dynamic system that modifies itself. This can be visualized as unrolling the updates through time, where the meta-learning algorithm now optimizes the initialization of the system. So how does this compare to other meta-learning systems? Here we look at memory-based learning, a very general class of meta-learning approaches. This approach is usually implemented using an LSTM, where the parameters correspond to the learning algorithm and the model or policy is encoded in the memory or hidden state H. For the self-referential architecture, we argued that it is capable of learning, meta-learning, and so on. The memory-based system can also be viewed as updating itself, because any update to its memory also affects future updates. Formally, we show in the paper that both approaches can simulate each other. So from a representational perspective, we have not gained anything from making our architecture self-referential. So what we really are interested in is getting rid of that meta-learning algorithm for the initialization. But how can we design a system that doesn't require explicit meta-optimization? And how do we guarantee that that system still improves over time and does not diverge? In this paper, we propose a very simple idea for a self-referential system that addresses this issue. As before, the system starts with some initialization, which is now not optimized, but random, and executes self-modifications. Crucially, each self-modification is stochastic due to the randomness in the policy, environment, or explicit input noise. And this creates a tree of branching solutions. And how these solutions are created is encoded in the self-referential system itself. But of course, we don't want to continue execution of all of these solutions. Instead, we want to ensure that self-modifications that work well reinforce themselves. To do this, we propose to simply assign more computational resources to better performing solutions. So we start out with some solution and generate new ones through self-modifications. And then from all solutions, we pick better ones with higher probability. We obtain new solutions and we repeat the process. Sometimes, with low probability, we also pick solutions with low performance. So the better the solution, the more computational resources we assign. In this scheme, solutions self-modify their behavior, their learning, and their meta-learning, etc. And there is no fixed meta-optimization scheme that defines how meta-parameters are adapted as a function of the performance metric. All these changes are self-proposed. In our experiments, we demonstrate some initial results. On a bandit task, self-modifications lead to an effective policy comparable to a simple hill climbing procedure. But on a slightly more difficult carpal task, we observe a larger gap to the baseline. This suggests that self-modifications adapt future self-modifications in a way that improves over the fixed way hill climbing modifies the parameters. Furthermore, on a non-stationary bandit task, we demonstrate that the system starts to learn how to learn when observing the reward as an input. In conclusion, we showed that self-referential systems can self-modify to solve various problems without any explicit meta-optimization. Finally, if you're interested in this line of work, please reach out to us.